Here we have some useful approximations. We are going to be using these approximations in Physics 262. You can find this file in our course folder for Physics 262, and it's called Useful Information Physics 262. So our goal in this video is to understand where these equations that are boxed, these approximations which are boxed, where they come from. But we're also going to be looking at some other stuff along the way, which I just think is pretty cool, and hopefully you will think so also. So we're going to start off looking at some information which is in Analytical Mechanics book by Fowles and Cassidy. This is coming from the appendix of the book because not only are these useful approximations used in our physics course, but they would also be used in an upper level mechanics course. So we're going to start off looking at the Taylor series, and we're going to look at this second equation here. So in the first equation, you have a function of x plus a. So in this second equation here, it would just be saying that a is equal to 0, which just makes it easier for us to look at. And for our purposes, it's not really going to matter. So what this equation is saying is you can take a function of x, and it could be any function of x, and you can approximate it using the Taylor series here. And so we're going to say, suppose we have a function of x, and it could be anything. Let's say that it looks something like this. I don't really know what I want it to do as we go far away from x is equal to 0, but it doesn't really matter. It could be anything. Okay, so now we're going to look at the first term that we have here, and that is our function of x when x is equal to 0. So that's this point right here. Now, if you're not moving that far away from x is equal to 0, so if you just have one term in the approximation, it would look like this. Now, if you're somewhere in this region here, that looks like a decent approximation. So the actual value of the function here is pretty close to the value of the function when x is equal to 0. Okay, now we're going to look at the second term in the series here. So this is x times the first derivative of x evaluated at 0. So the way that works here is, oh, and here you can see instead of doing a prime symbol here, they have n. So this means the nth derivative with respect to x of your function, but then you're going to evaluate it when x is equal to 0. So first you take the nth derivative, and then you say x is equal to 0. So we would take the first derivative of our equation here, which would be the slope, and then we say, so if you just take the first derivative, if you look here, it would be the slope of your function at this point. If you look here, it would be the slope of the function at this point, but we're going to say when x is equal to 0, which means the slope of the function at this point here. Okay, so with two terms in the series, you have this point here plus x times the slope at this point here. Now, if you had a linear function, this would be, okay, so the first term that we have here is the function evaluated when x is equal to 0, which is just this point, which is the y-intercept. And then you take the slope, so this would be f of x is equal to the function when x is equal to 0 plus x times the derivative of the function with respect to x, evaluated at 0 only for this case because it is linear. It doesn't matter that you're evaluating when x is equal to 0 because the slope is not changing at all. So this is the y-intercept, so let's call that b, and then you have plus x times this, which is the slope, so that looks like y is equal to mx plus b. And so now this isn't just an approximation, this is actually your linear equation. For our situation here, it's still just an approximation, and it's a better approximation now, so you can go farther away from this point here and still have a reasonable approximation. But if you continue using the series, so taking the second derivative is now going to give you information about the concavity of the function at this point here, and so it will be an even better approximation. And if your function is linear, the second derivative is going to be 0. All the terms after this are going to be equal to 0, so you're not improving your equation at all by continuing to add terms because the rest of them are all 0. Okay, but the more terms you add, the better the approximation gets in this case here. If you look on the PowerPoint, which I will be including in the email that I send out to you with the link for this video, on the second slide of the PowerPoint, there is a graph, and in green you have the cosine of x, and then it's showing you if you do 4 terms, it would be you'd be approximating the cosine function, and it would be good, but only in a small region. And if you do 6 terms or 10 terms, it's a better approximation in a larger region. So you can look at that on your own. Okay, so now what we're going to do is look at what we would have for the Taylor series for e to the x. Now this one is pretty easy because the derivative of e to the x with respect to x is just e to the x. Same thing for the second, third, fourth, and so on derivatives. And when you evaluate it, when x is equal to 0, you just get 1. So anytime you're taking a derivative here and evaluating it at 0, this is just going to be 1. So then, what we get here, this would just be 1. This would be x times 1. This would be x squared divided by 2 factorial, and so on. And this is x to the nth divided by n factorial, and then we keep going. Okay? So we're also going to look at what we would have for sine of x. So we evaluate sine of x when x is equal to 0, and we just get 0. For the next term, we take the derivative of sine of x, which is cosine of x, and we evaluate that at 0, so that's just 1, and we multiply that by x. And then for the third term, we'd have negative sine x, and then we evaluate that at 0, and we just get 0. So the third term is 0. And then for the fourth term, we would have a negative cosine x evaluated at 0. That would give us negative 1. But okay, we are on the fourth term here, so that would be x to the fourth divided by 4 factorial. So every other term is 0. And then for the non-zero terms, the sign is going to alternate between being positive and negative. So you could figure out what the rest of that looks like. Okay, then for cosine of x, when we evaluate that when x is equal to 0, we get 1. You take the derivative, you get negative sine x evaluated at 0, that's just going to be 0. And then you take the second derivative, which would be negative cosine x, so now we have a negative sign. And that would be times x squared over 2 factorial. And then the fourth term is going to be equal to 0 because you'd be looking at sine of 0, which is 0. And then this has a similar pattern to sine of x. Every other term is 0, and for the non-zero terms, the sign is going to alternate between being positive and being negative. Okay, so that brings us to this point here. And now we're going to look at what would happen if you set x equal to I times theta, where I is the imaginary number. and that is equal to the square root of -1. So if you make that substitution in the expansion for e to the x, you get e to the I theta is equal to 1 times x is equal to I theta. And then this would be x squared, so that would be I squared times theta squared, and so on. Now, if you have I squared, that's equal to the square root of -1 squared, so that's equal to -1. And if you take I squared and multiply it by I, that would be I cubed, and that's negative I. And then if you do I to the 4th, that would be -1 squared, so then you're back at 1. So they say here, for I to the nth power, if n is equal to 0, or 4, so we could also say, yeah, if I is equal to 0, that would just be 1. So if n is equal to 0 or 4, you just get 1 back. Or, okay, so 0, 4, 8, 12, 16, and so on. When n is equal to 2 or 6, you would get -1. When n is equal to 1 or 5, we get I. When n is equal to 3 or 7, we get -I. So we could take, oh, I didn't write it down. We could take what we have here and rewrite it. And whenever n is even, we can move those terms in this set of parentheses here. And when n is odd, we can move those terms into the parentheses that we have here with an I in front. And because of this, what we have here, if you look at the even terms, the sign is going to change. So that would be looking at this and this. So -1 and 1, and you're going back and forth between these two. When you're looking at, between these two, when you're looking at the even terms. So the sign is changing, and instead of having an x squared over 2 factorial here, now it's a theta squared over 2 factorial, and it's negative. Similarly, with the odd terms, the sign is going to change, and you pull the I out front. But compare that to what you have here for sine of x and cosine of x, and you will see that what is in parentheses here is just cosine theta, and what's in parentheses here is sine theta. So we get e to the I theta is equal to cosine theta plus I sine theta. And we're going to look at this more in just a minute. Before we do that, for our useful approximations, you can derive these approximations from the Taylor series expansion, but you can also get them from the binomial series, which they have here. So we're looking at the last 3 approximations that we have, and for these 3 approximations, this would be 1 plus x to the 1/2 power. So in this equation here, n would be equal to 1/2. When you have 1 over 1 plus x, that would be 1 plus x to the -1 power. And so if you do a Taylor series expansion for that, you have 1 plus x to the n. And then let's go back and, we can look at this here. Okay, so we evaluate the function when x is equal to 0. So that first term, if x is equal to 0, this would just be 1, and it does not matter what the power is, because 1 to any power is still going to give you 1. And then we take the first derivative, but after taking the first derivative, we set x equal to 0. So this would be plus n times 1 plus x to the n minus 1, but evaluated when x is equal to 0 would again give you 1 to the nth power, which is just 1. And then I have to multiply by x. And you could keep going. And, well, they showed what the next term would be down here. But for our purposes, it doesn't really matter because we are going to say when x is very, very small, so much, much less than 1. So there's 2 less than signs here. So it's not just that x is less than 1, it's much, much smaller than 1. So if x is much, much smaller than 1, then we're just going to say what we have here. 1 plus x to the nth is approximately equal to 1 plus n times x. And then from this, you could say for the square root of 1 plus x, n would be equal to 1/2, so you get 1 plus 1/2 times x. And here, n is equal to -1, so we'd get 1 minus x there. And then you can also make the following approximation here. So, and I guess you could just get this approximation from the one that we have here. So if you take this and you just take the reciprocal of both sides, you'd get this equation here. So these 3 approximations we are going to be using, and now you know where they came from. Okay, and now it's time for some more stuff related to what we have here, which we're going to go over just because I think it's interesting. Okay, now if you want to follow along with the PowerPoint, this would be the second to last slide on the PowerPoint. Okay, so suppose we have a circle here, and the radius of the circle is equal to r, and I choose a point here, then the x-coordinate for this point would be r cosine theta, and the y-coordinate for this point would be r sine theta. But we could make this the complex plane, so on this axis we have real numbers, and on this axis we have imaginary numbers, and now our point here can be written as z is equal to x plus I, y. And for this case, x would be equal to r cosine theta, and y is equal to r sine theta, so this is r cosine theta plus I times r sine theta. And this is equal to z. I can also pull the r outside, so I have r times cosine theta plus I times sine theta. But we said up here cosine theta plus I sine theta is equal to e to the I theta, so this is r times e to the I theta. So your complex number could be written like this, z is equal to x plus I theta, or you can write it as r times e to the I theta, where r is the radius of the circle that you have here, and theta is the angle that you have here. And now, if we say the radius is equal to 0, okay, so we have a circle here, it's supposed to be a circle, and the radius is equal to 0. And we're going to look at 4 different points on the circle. So we're going to look here, and this is when theta is equal to 0 and r is equal to 1. So we would have, for this point here, cosine of 0 plus I times sine of 0, but sine of 0 is equal to 0 and cosine of 0 is equal to 1. So this point in the complex plane, this point is equal to 1. And we could also write this as, because the radius is equal to 1, we could say at this point z is equal to 1 times e to the I, well, that would be 0. I times 0 would be 0. So this is equal to 1. Okay, now let's look at this point over here. So because I have real numbers on this axis here, I would say that this point should be equal to -1. And the angle here is equal to theta. So for this point, I would have, well, the angle is equal to theta, yes. Theta is equal to pi. That's what I meant to say. So this would be cosine of pi coming from this equation here. R is equal to 1. So this is cosine pi plus I sine pi. But sine of pi is equal to 0, cosine of pi is equal to -1, so this is indeed -1, but you could also write it using this expression here, and you have r is equal to 1, so this is e to the I pi, which is equal to -1, and you can rewrite this and get Euler's identity, so this is e to the I pi plus 1 is equal to 0. Hooray! All right, so now we have 2 points left to look at, and then we'll be done. So we're going to look at this point here and this point here. For this point here, we have theta is equal to pi over 2. So this is cosine of pi over 2 plus I times sine of pi over 2, but cosine of pi over 2 is equal to 0, so this is just equal to I, and you could also write this as 1 times e to the I times pi over 2. So not only is e to the I pi equal to -1, but e to the I times pi over 2 is equal to I. And then, I mean, this one really didn't come as a surprise. E to the 0 is equal to 1. And then down here, we have the angle is equal to 3 pi over 2. So this would be cosine of 3 pi divided by 2 plus I times sine of 3 pi over 2. Cosine of 3 pi over 2 is equal to 0. Sine of 3 pi over 2 is equal to -1. So this is equal to -I, and also we could write this as r is equal to 1. Theta is equal to 3 pi over 2. So e to the I times 3 pi over 2. This is all in the exponent there, is equal to -I. Okay, so that concludes this video, and the important thing for you to take away from this video is that these 3 approximations can be used based on the Taylor series or the binomial series when x is much, much smaller than 1.